Sorry for the late start, technical problems. So I'm going to be talking about machine learning and specifically how machine learning is applied to cybersecurity. And I'm planning on doing, basically the plan is to do a high-level overview of machine learning. And I promise that there won't be any math, although I might be lying. There might be a couple equations. However, I want to make this really high level and leave out as much math as possible because I think one barrier to really understanding machine learning, which I think understanding machine learning is important for being able to evaluate the models and separate some of the hype from all of the other stuff that we see out there. We see a lot of specifically AI hype out there. And I'm going to try to avoid a lot of boring slides filled with terminology, although there might be a couple. Machine learning does have a lot of terminology, but I'm going to try to cover the terminology as I'm going through an example, because I think examples are the best way to see how things work. And so really what I want you to get from this talk is that you can look at a machine learning model, you can read a paper, you can read an article, you can read the news about the latest and greatest AI deep learning model and kind of determine like be able to ask skeptical questions like, is this reality? Is this is this just like being able to just question it and understand the metrics that are used to evaluate these models. And just quickly about me, so I have a PhD in chemical engineering, I have a bachelor degree in electrical engineering, and you might be wondering like, okay, well how do you get from engineering to data to like presenting at a security conference? And what a lot of people don't understand about engineering is that it has a lot of data. Like engineering kind of has the same problem as security in that there's just a lot of data generated. And so I've spent a huge chunk of my career creating machine learning creating models, like data models to mathematically model data, to get answers from the data, and really just get what we need from the data. I'm currently working as a senior data analyst and a data steward at the state of Utah. And kind of as part of that, I teach OSINT skills to state investigators. I also teach a after-school cybersecurity program for a company called WorkEd, and they're pretty awesome. I love what they do. They basically target high school kids that are interested in going into cybersecurity or tech as a career and kind of get them on the right path to where they can do that without all of the traditional hurdles people sometimes have getting into a career. And I also volunteer for Trace Labs, and Trace Labs is a nonprofit organization that uses crowdsourced OSINT to find missing people. All right, so the first question is, what is machine learning? And I just shout out some answers of like what you've heard about it or what you think it is, or if you know what it is. It could be like a one-word answer, a couple word. Voodoo. Voodoo? That's a good one.
Math.
Yeah, it's a lot of math.
Is it part of AI, or AI is part of that? One or the other, or both?
Yeah, we're going to get to that, but yeah, it's definitely related to AI. All right, well, we can read this big, long, boring spiel about it on Wikipedia, or we can just jump to machine learning is about making predictions. That's really all it is. Like, it's just about making predictions. And so I've seen a lot of long definitions of what machine learning is. I've seen like a lot of really convoluted definitions that they have like all these words to make it look like fancier than it is, but all we're doing is making predictions. We're just taking our data and we want to predict something. So just keep that in mind as as we go through the talk, and just remember, like, we're just talking about making predictions. And so then, isn't machine learning AI? So this is where there's a lot of confusion, because there's a lot of hype now, like there's a lot of buzzwords now, like AI is definitely a buzzword, machine learning is a buzzword, data science, big data, like basically all of them. So sometimes it can be really hard to distinguish, like, well, what are we actually talking about? And so really AI is about mimicking human intelligence. So it's much more broad than machine learning. Machine learning is, again, if we just come back to, machine learning is about making predictions. And where machine learning ties into AI is that most AI algorithms use machine learning. So that's where the connection is, but machine learning isn't really AI, it's that AI uses machine learning for a lot of their models, and then AI is about something broader, like creating something that is basically mimicking human intelligence. So isn't machine learning statistics? Well, if you want to get into a big fight, go ask some people on Reddit this question. So there is a difference. Machine learning is its own field, and the machine learning has actually been around for a long time. The first algorithms, and it was a really theoretical field for probably since about the 40s, really the 50s, and it didn't really become practical until more recently, mainly because of the huge increase in available data and also the increase in computational power. So these the machine learning was largely theoretical, probably up until about 15 or maybe 20 years ago, but it's really been within the last 10 years that it's really taken off. And it's really because the model existed in the 50s, but it would take a computer thousands of years to run the model, so it wasn't really practical. Whereas the machine learning, we just come back to, machine learning is about making predictions. Statistics is about a lot of other stuff. Statistics is a study of data. So we certainly use statistics within machine learning, but machine learning is just about making predictions. So some people, and I might get into trouble for saying this, but some people say that machine learning is statistics without error checking. And we're certainly going to check our model, but we don't care if the statistics are exactly correct as long as it's making correct predictions. If it's making correct predictions, that's all that matters. Okay, so how is machine learning different from traditional programming? So who here programs, or has written programs? So what do you normally do when you write a program? Just give an example. What are you telling the computer to do?
Move data.
Yeah, move data. I guess get a little more specific. Are you you're telling it, you're giving it some if and else statements. You're telling it what to do, right?
It's deterministic.
Yeah. Yeah, so with traditional programming, we're basically giving the computer or the machine the rules and the data. So we're giving it rules and data, and then it's giving us the answers. With machine learning, you have to kind of rethink how you're programming. With machine learning, you're giving the you're giving the machine or the computer the data and the answers. And what the computer is doing is it's giving you the rules. So it's basically writing the rules. So all of these if-else statements we write, or like if you're doing blacklists or whitelists or anything like that, you're not actually writing those now. The program is writing those based on the data that you gave it and the rules that it determined from that data. And so the difference is with traditional programming, it's very rigid. You can't easily change the rules. You have to go in and edit your code, which can take a while. with machine learning, it's flexible because it can adapt. So you can feed like when you feed new data into your program, we're going to go through an example, so you'll see this in action. But the machine or the computer will rewrite those rules for you. So basically update the program just on getting new data. And I do have kind of a star here. So we only have answers with supervised learning, and I'm going to define supervised and unsupervised learning next. So in machine learning, we have what's called supervised learning and unsupervised learning. And sorry, this is one of those boring terminology slides, but we have to have a few. Supervised learning is our model is trained using pre-existing data. And I just said a whole lot in that sentence that I want to define a few things. So first of all, what is labeled data? Like, does anybody know what labeled data is? Yeah, it's data that's labeled. So
that it knows what it actually is?
Yeah. Yeah, so it knows what it is, and that's a good answer. And so like a specific example of that is, let's say that we're trying to identify malware. So you might have a data set that has benign files and files that are malware, and they'll actually, like there will be a column with labels. So it'll actually say like, this one's malware, this one's malware, this one's benign, this one's benign. So that's one way to think of it. You could also spam emails. So like you could have a data set with emails and they could be labeled as like spam, not spam, spam. So that's what it means by that your data's labeled. Like we know what the data is. And we're going to talk about trained in a minute. And the model is what you're building from the data that you're going to use to make predictions. So just think of it like that. The good thing about supervised learning is we can mathematically prove how well the model is doing. And we're going to see that play out when I do the example. So I think that'll make a lot of sense when we get to that. But just remember right now, supervised, you can prove how well your model's working. Labeled data is a challenge in cybersecurity. And so you have to either label your own data or sometimes get creative. And one issue is sometimes people get creative by using publicly available data sets. So there's a lot of security-related labeled data sets on GitHub, Kaggle, like just places where you can download public data. And there is an issue with people training cybersecurity-related machine learning models using those public data sets. And we're going to see why that can be an issue a little bit later when we talk about data poisoning. But I just want to point out that like the labeled data it can be pretty intensive to get labeled data or to do it yourself, and so it's an issue. And then it's just some specific things you can do with supervised learning, and this isn't all the things, and you can also do some of these with unsupervised learning that we're going to talk about next. So these are just some examples, not and all, but like identify network risks, predict or classify security threats, and detect malware, some examples of things you can do with that. Unsupervised learning, the model's built without labeled data. And so if you think about what we just said, like talked about with labeled data, this is data that doesn't have the answers. So we might have a data set full of URLs, and we don't know if they're malicious or not. Like we just know that we have these URLs. And so we're going to use that data set to build our model. And I'm going to talk about the type of machine learning that you would use to do that next. But really the main difference is you can't mathematically prove how well the model is doing with unsupervised learning. And that's mainly because we don't know what the answer is. Like, that's really the main reason. And unsupervised learning can be good for identifying new threat patterns or detecting new types of malware. And the reason why is because if it's a new type of behavior or a new type of malware, there might not be a labeled data set with that in it. So therefore, it would take a supervised learning model might not detect like a new type of malware just because it's not recognized by the model. So problem types, classification. This is a type of supervised learning. And this basically just takes your data set and it uses it to build a model that will predict what category data belongs to. And so specific examples are like detecting like spam detection, malware detection, malicious URL detection. And the other type of machine learning problem type is regression. And I will say regression is useful in cybersecurity for some things, but classification is used a lot more. So most problems in cybersecurity are some sort of classification problem. Regression is also supervised learning, and this predicts a continuous value. So the example I have is network risk scoring. So the difference between the regression and classification is with regression, you're getting a continuous value. So like network risk scoring might be somewhere between 0 and 100. I'm not really sure how it would be scored, but that would be an example, like you would just get a number. Whereas with the classification, you're gonna get like a specific class, like it's either gonna be, it's malware or it's not malware. So that's the difference. And then clustering is unsupervised learning. And this takes your data and predicts discrete classes. Or it basically takes, like, so an example is like with the URL file that I mentioned earlier that might not be labeled. We're gonna take that data and run it through our algorithm. And what it will do with clustering is try to find how the URLs are related to each other and then create different clusters with those URLs. And then we can determine like, okay, if this cluster has malicious malware or malicious files, then we can assume anything that resembles those is also malicious. So that's kind of how clustering works. But it also comes back to that we don't know for sure if they're malicious because we don't have the answer. But this is where this can be useful for detecting new types of malware or like new types of patterns that might be malicious. And then dimensionality reduction is also unsupervised learning, although this is often used in combination with one of these other three. And what this does is it reduces the number of variables or features in your data set. So the machine learning example we're gonna do is only gonna have like about 7 variables or features. So we wouldn't need to reduce that, but a lot of these models will have variables or features that you'll have like 100 or you'll have 1,000 or like with genome stuff you might have 100,000. So you really want to, so that's where you would really want to reduce the number of variables and so dimensionality reduction will pinpoint the variables that aren't really contributing to your model so you can remove those, or it'll remove them. And so that can also help remove noisy and irrelevant data. So I'm going to go through these really fast because I want to get to the example. So linear regression, and these are types of algorithms that are used. So what I just finished talking about are kind of like the types of machine learning. So this is getting a little more specific in the algorithms that we're using that are, so linear regression is supervised learning, like we need labeled data to do linear regression. But this is basically, like you've probably seen linear regression. You've probably seen like some points on a graph and then you draw a line through it. Like, have you guys seen that? Yeah, so that's basically what linear regression is. And so if you just have one variable, then you would just get a line. But you can also have multilinear regression, so you can have multiple variables in a regression model, and you can use linear regression if your data is linear. So that's really the assumption for that model. Logistic regression is also a type of regression, but it's also a classifier. And this is also supervised learning, like we need a labeled data set for this. And this is kind of, some people get confused because they're like, well, why is it predicting like spam or not spam? When it says it's a regression, shouldn't it be predicting a number? And it does predict a number. What it predicts is a probability that something is spam or not spam, and then depending on how you've defined what your threshold is for, like, say you're like, okay, if it's 0.5, or if it's 50%, if the probability is 0.5 or less, then it's not spam. If it's 0.5 or greater, then it is spam. So then the model will take that probability and classify it based on what the probability is. So it's kind of how that works. Decision trees are what we're going to play with later. Decision trees are a pretty basic model, but they're really useful. Like, they're the basis for a lot of other models. And one thing that is really useful about them is we can see how the computer is making its decision, like how it's categorizing things. And that is something that can be important in security because some models you can't tell how it made its decision. And this is, and I'm going to talk about this a little bit later, but this is actually a problem with like neural networks and some of the deep learning algorithms that are being used. We know that it's using math. Like, it's not voodoo. But we know it's using math. We just don't know exactly what equation it came up with that it's using. And so that's where it's not really I don't consider it a black box because we know it's using math. We know, but it's not transparent about how it's making the decision, whereas decision trees are really transparent. Like, we can see exactly how it made its decision, so it's pretty useful. Support vector machines are, these are good if you have data that has outliers. So this is, well, I have to explain what outliers are. Outliers are basically things that are like quite a bit different from what the average of your data set is. So it's things that it might be real data, but it's like way different from everything else. And those can kind of skew your model. So support vector machines are good at handling that. They're good at modeling nonlinear data. And so their classification, they can do classification and regression, so they're pretty useful. And the example I have here is predicting malicious IPs. K-nearest neighbors is also a classification algorithm. And this basically just looks at how things are similar to like neighbors and forms different groups. Like, it just groups things together. So this can be used for this can also be used for like spam detection, fraud detection. I have the facial recognition, although that is probably mostly done with more of a deep learning model. So k-means is an unsupervised learning model that does clustering. And so the difference between k-nearest neighbors and k-means is that k-nearest neighbors is for classification like a supervised learning, so we need a labeled data set. K-means is unsupervised, so we don't need a labeled data set. The k is just, the fact that they both have a k doesn't mean that they're related. They're pretty different. They both have a k because the k represents how many clusters you're creating. So for instance, with k-means, if you say, I want to do 10 clusters, then it would be 10 means. So that's just a parameter in the model. Random forest is basically a forest of decision trees. So we're going to, and I don't want to spend a ton of time on this because we're going to see a decision tree in action later. So as we go through the decision tree, just imagine having like hundreds of those. And so a random forest really builds on like the decision tree model, and it can be a really great, really good model. Neural networks, so this is all of the deep learning models, and neural networks are based on what biological networks in the brain might be like, but really they classify, they can predict data that is really nonlinear, and so we've seen how they're, like with some of the AI stuff that's out there now, we've seen how they're pretty useful. So they are useful. So they're used for anomaly detection, intrusion detection systems, also like facial recognition, recognizing images, so they're used for a lot of things. All right, so now we got through all of the terminology. And I hope that I didn't just drive you guys crazy with machine learning terminology. But now we're going to do an example. So this overview, and we're going to go through each of these steps. I want to show you step by step how to build a machine learning model. And so this is what's called the machine learning process. So there's a process to building the model. And so the first step is, what do you want to predict? And so I always pause there because you don't want to get through the steps, and I've seen this happen. You don't want to get through the steps of you've collected your data, you've put a lot of work into it and time and money, and then it turns out you don't have the data that you need for what you want to predict. So it's really important to clearly define what you want to predict. Like, what data do you need? And are there legal implications? Like, for what you're wanting to predict, do you need data that there might be some company policy or legal, like there could be a law that you can't use that data for machine learning. So you need to make sure that what you want to predict and what you're going to be able to have the data to do that. It's going to be consistent, like will you be able to get more data? Is the data biased? Data bias can be a huge problem. And can you legally use that data? All right, so what we're going to do is we're going to predict with a 90% accuracy who clicks or does not click on a link. And we want it to prioritize correct predictions when the link is clicked. And we've also determined that all of the data we need is available and it doesn't have any legal or policy restrictions. So we're good to go. We can basically do anything we want with this data. So the next step is we need to collect our data. So we're going to do that. And who in here saw this link floating around? Did anyone? I think they're all I think everybody who clicked on this link is at the tinfoil hat talk. So good for you guys. All right, so yeah, we collected our data, and here's our data. So the first data point was, do you attend SAINTCON? And so this is going to be a yes or no. Are you an iPhone owner? This is also going to be yes or no. So this is categorical data. Self-reported that you like mini badges. And so this is like, Have you posted in the Discord chat that you like mini badges? Have you gone around and told people that you like mini badges? It's basically like how much oversharing have you been doing about mini badges? And so this would also be a yes or no. Are you a Windows really good user? And anybody in here a Windows really good user? Anybody? Okay, I think they're all at the tinfoil hat talk too. All right, so that would also be a yes or no. Mini badge collection size. So this is going to be a numerical value. So this is the number of mini badges in a collection. And number of mini badge creator posts per week. So this is the average number of posts that someone is making in the mini badge creator Discord channel. Number of days that you wear a black t-shirt per week. So this is the average. So this is the average number of days per week that you wear a black t-shirt. And so this could be anywhere between 0 and 7. And finally, we have labeled data because we know if they click the link or not. So really, these first, so how many is this? 2, 3, 4. So our first 7 variables are the features. Like this is what we're going to be using to build our model. And so these are the features that are going to predict whether or not someone clicked on a link. And since we have labeled data, we know if they clicked on it or not in this data set. All right, so now we need to go to the next steps. So we know what we want to predict. We collected our data. We understand the data, and like this is just like we did some summary statistics on it. We're not going to do those during this talk because there isn't time, but I did do some summary statistics on this data. And I can say that there is a link between like the tinfoil hat talks and Windows RG users. All right, so now we're going to clean the data and do some feature engineering. And what's meant by cleaning the data? This is another machine learning terminology that you'll see floating around. And a lot of people are probably like, well, what in the world does that even mean to clean data? What it means is data sets are messy. And especially in cybersecurity, data can be really messy. It can be missing a lot. It can be missing a lot of values, have a lot of duplicates, outliers, and inconsistent or invalid data. So in our particular set, we're not missing any values, so we don't need to worry about that. But if you were missing values, you would just figure out what you want to do. Like if you have a large data set, you could possibly just delete those rows that are missing values. But if you don't have a lot of data, you might want to figure out a way to add those in somehow, like either taking the average of other values. There's a lot of ways to do it. We don't have any duplicates. We don't really have any outliers either. And I think our data is pretty consistent, so I think we're good with fixing the inconsistent or invalid data. Feature engineering is feature selection. So this is where if we want to remove certain variables that might not be contributing anything to the model. Since we only have like 7 variables, we're probably not going to run into an issue where we want to remove variables, but like if we had a lot more, we might want to. Data scaling and normalization. This is basically putting all of your data on the same scale. So some models, sometimes you can run into trouble if you have one variable that that's on a scale of like 10, and then you have another variable that's on a scale of like 100,000. If you try to use those together in your model, it can cause inconsistent results. So scaling and normalization would basically be like putting all of your data on the same scale. Dimensionality reduction. This is kind of this like feature selection. So this is removing features. This could also be combining features So instead of 2 features, you would just have one that represents both of them. And then encoding. So we do need to do something with our data to make it usable in a model. So if you noticed, we had yeses and nos. And do you think we can just put yeses and nos into a mathematical model? Like, do you think that that's going to work?
No, it'll do junior high math, which is where I
Well, yeah, so if you have yes.
algebra, right?
Yeah, well, I'll just say, like, if you try to do that, you're going to get a big fat error. So anyway, we need to encode our data somehow. So going back to the data, and I kind of have the answer on this slide, I guess, but we're going to encode it with, we're going to make all of the no's zeros and all of the yeses ones. And so we've done that, we're good with that. Now we're going to select our model. And this says select model. A better word would probably be select algorithm, but I used model here because that's like people kind of use these interchangeably, so you'll probably see both. But this is where we're selecting our algorithms. So this would be like, the algorithms are like the logistic regression, the linear regression, the decision trees, like all of those. This is where we select that. And the one you select is dependent on your data. So that's why you need to do like the EDA and the collect, like understand your data, because that will tell you what model might be best to use. And we're going to use a decision tree. And the main reason is because it's explainable, so we can see how it arrived at the decision. And it can use both categorical and numeric data. So remember, we have both, so we need to pick a model that can use both. And not all models can use both, so that can be a deciding factor for your model. And also, like, if we look at, and these plots are pretty small, so don't stress if you can't really see them. The point is just, like, if you look at the big picture of them, the data looks really nonlinear. Like, I don't see any specific place where I can draw a line, where I can, like, draw circles around things to get all the blue and orange square or circles like in one spot. Like, I don't really see a good way to separate them. So I'm pretty sure that this is nonlinear data, so we need a model that can model nonlinear data. All right, so this is the easy part of the model. The hard part, and the part that takes about 90% of your time, is collecting the data, cleaning the data, feature engineering. Now, once we're to the point of like basically building the model, this is like 10% of it. I mean, this is the easy part. What we're going to do is we have our data, we've encoded it, it's good to go. We want to split the data into what's called training data and testing data. And it's really common to do either a 70-30 split or an 80-20 split. And so we're going to do a 70-30 split. And what the training data is, that's the data that we're going to use to train the model. Like, so that's what we're going to run through this decision tree algorithm, and it's going to build a model using a decision tree. And then we're going to use the testing data. We're going to put the testing data through our model and see how well it predicts that testing data. And remember, we can do that because it's labeled, so we have the answers. All right, so let's do that. And this is what we get from our decision tree classifier. And I did limit this to three levels deep just so we can see it. But I have some questions. So who here has less than 157 mini badges? Raise your hand. All right. And who here wears black t-shirts less than 4.5 days per week? Okay, so all of you with your hands still up, the model predicted that you clicked the link. All right, let's try that again. So how many of you have less than 157 mini badges in your collection? Raise your hand. How many wear black t-shirts more than 4.5 days per week? Couple. And I know you attend SAINTCON because you're here. So it predicted that you clicked the link. All right.
You gotta tell them about the guy in China.
Yeah, I did. I did have a guy in China click the link at the PCB factory where I made the mini badge that had the link. All right, so who has more than 157 mini badges? You're the only one? Well, we're going to change that because I think I have enough mini badges for everyone in here. All right, and I like this one. Do you post less than 9.5 times per week in the mini badge creators Discord group? If the answer is yes, like basically you have a lot of mini badges, you're basically lurking in the forums, you're not posting very much. It's the lurkers that click on the link. So be wary of them. All right. What question should we be asking at this point? Like we just went through this model. I just told you, I just showed you how it was making predictions. What, there should be some warning bells, like what? Yeah.
Is it the 90% accurate target rate we were getting, or greater than 90% accurate?
Yeah, we don't know if we've hit that yet, right? Yeah, so that's it. How do we know if this model is any good? So what we're going to do is evaluate the model. And so this is where our test data set comes in. So we're going to run our test data set through this model and see how well it predicts what's in the test data set. And in order to see in order to evaluate this, we need to look at the confusion matrix. And the confusion matrix is called the confusion matrix, not because it's confusing, it's because this is where the machine gets confused. This is showing us where the machine didn't correctly predict things, and so it's confused. So we're not confused, it's the machine that's confused. All right, so basically what we do is we just put the actual and predicted together, and if the actual was true, that someone clicked the link, and it predicted that they did, that's called a true positive. If the actual was that they actually clicked the link, but the prediction was that they didn't, that's a false negative. That's also called a type 2 error. If the actual is negative, that they didn't click the link, but it predicted that they did, that's a false positive, so that's a type 1 error. And if it's negative, well, if the actual is that they didn't click the link and it predicted that they didn't click the link, that's called a true negative. And these are the only, so I put up the other equations. This is the only math I'm going to show you in this entire talk. So, but I think seeing the math for these equations can help you understand what these metrics actually are. So accuracy is basically just the total number of true positive and true negative divided by the total number of samples. So that's just a percentage of how many correct predictions the model made. Sensitivity is also called recall and true positive rate. And this is the number of true positives divided by the total of true positive plus false negative. And basically what this is telling us is how good the model is at predicting when they click the link. And then the opposite of that is specificity. And this is the true negative divided by false positive plus true negative. And this is basically how good the model is at predicting when they don't click the link or when something doesn't happen. So let's analyze our model. So our accuracy was 78%. Our sensitivity was 71%. So that means that it predicted about 71% correctly when people clicked on the link, and it predicted about 80% correctly when people did not click on the link. So that doesn't meet the metrics that we wanted. So let's think about this. What if we did this to our model? Like, what if we just add more, like, what if we just make it more complicated? Do you think this would give us a higher accuracy?
Not necessarily.
Exactly.
Be more complicated.
Yeah, and this is one reason why I wanted to give this talk, because vendors try to push stuff that looks really complicated and like, it must work, right? Well, actually, this doesn't work better. So if we compare this to our original tree, our accuracy went down, our sensitivity went down, our specificity went down. Well, really, and the question is, well, why? And it's because you overfit the model. So overfitting is when you almost exactly predict the training data with your model. And so if we were to run our training data through this model, we would probably get like in the high 90s as far as accuracy. But when we run the testing data through it, our accuracy goes way down because it's overfit. And just some solutions to overfitting: a different algorithm, add more data, try removing features, adjust hyperparameters. And if you think about it, my original model, I did have a hyperparameter that limited the depth of the tree. So the opposite of that is underfitting, and this is when your model does not fit the training data well. And so it basically makes poor predictions. This model, like when it's underfit, it's probably about the same as random guessing. And I'm going to skip some of those solutions just for time, but basically one thing you always want to do is you want to make sure that your model does better than random guessing. And sometimes that can be really hard. Like if you imagine a scenario like, let's say that you have a network that maybe 3% of the traffic is malicious and you're trying to predict malicious traffic, and you create a model that predicts that all traffic, that there's no malicious traffic. It predicts nothing is malicious. Technically, that model is 97% accurate. So that's what you want to watch out for, things like that with accuracy, and always look at multiple metrics and really evaluate your model. And I think I'm going to skip. So I was going to do like run this model again with some other algorithms. So the decision tree, k nearest neighbors, and random forest. And this is really what you would do in real life building these models. You would try multiple algorithms, you would adjust hyperparameters, and this is a really iterative process. So even though I just have lines going one way, this is really iterative. It's common to go back repeatedly to previous steps. If you're building a machine learning model with the waterfall method, you're going to end up with a really bad model. So it's really iterative. All right, well, why are we using these models when we can just use deep learning convolutional neural networks? Any thoughts? Like, why, if we could just use this, like convolutional neural networks, why would we want to use a decision tree?
Because the neural networks are deterministic and there's no like insight into what they're doing.
Yeah, that could be a reason. Like if you need to know what, like you need transparency in the decisions. So yeah, that's one reason. I had a few reasons here, but one of them is like if you like large bills from Amazon for your instance, neural networks are really like processor intensive, and so if you can use a simpler model to adequately model your data, you don't want to use a more complex model. And the other thing is, if your model is, if you don't have a lot of data, and when I talk about data, like a lot of data, like big data is what a neural network would do well on. If you have less data than what might be considered big data, a lot of these simpler models actually perform better. So this is something you want to evaluate though. So I have the simpler, basically the reason to use like a neural network or a deep learning algorithm is that simpler algorithms don't adequately model your data. Like, that would be the reason. And then I'll just go through this quickly. So there are some challenges with machine learning and cybersecurity. And I think that some talks are going to be hitting on some of the issues where they become an attack vector. So I'm intentionally not spending a lot of time on that. But basically, there's issues with the data being sensitive and siloed. So it can be difficult to get enough data to build a high quality model. Data's often in hard to use formats, and I'm looking at you log files. They're usually in formats that they're not standardized and they can be difficult to get into a format to feed into a machine learning model. The model interpretability, so that's where, do you need transparency? If you don't, then, but sometimes you might. That might come down to, if an incident happens and there's a lawsuit and it comes up, well, why didn't you make this decision? It's well, this model that we have no idea how it works told us this. That could turn into a legal issue. So those are just things to think about. Lack of labeled data, and then the additional cost of running computationally expensive models, so that would be any of the deep learning models, and it can become an attack vector, so data poisoning. Based on what we've seen today, do you guys think it would be a problem if a threat actor had your training data? Yeah, they could do all kinds of things to it. So they could, if they had direct access to the data, they could change some labels. They could add, they could change some of the features. And so data poisoning is a huge challenge. If they don't have direct access to the data, a lot of models are retrained on a pretty frequent basis with new data. So they could inject, not malicious data, but data that will feed into your machine learning model as training data and cause it to make incorrect predictions about certain things, if they're trying to make it so it won't detect a certain type of malware. And one thing I do want to point out with data poisoning is it doesn't take changing a lot of data to cause a huge change to the accuracy. So I've seen some numbers that just a 3% change in your training data can cause up to an 11% change in the accuracy. So it can be a pretty big deal. And then model extraction and evasion. And we're out of time, so I'm not going to talk about those. But thank you for coming. I think we have some mini badges for you guys. And there's might be time for one or two questions if anybody has any questions. All right, well, thank you for coming, and